Welcome to the Cosmic Pie Podcast, episode 36, season number 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the University of North Dakota here in Grand Forks, North Dakota.
We're starting to feel like, we might actually get a winter.
It is November, Robert.
I know.
November.
But, we're still above freezing.
Now, you're one of those guys that hope the climate change would be such that you could run around in your swimsuit in December outside, right? And not freeze.
No, I think it should be freezing right now.
Now, we do have a live chat feature that's running, so if you have any questions or comments that you would like to make throughout the podcast, that's the beauty of being here live with us.
Yep.
So we usually typically broadcast every Tuesday at 5 p.m. Central Time.
Mm-hmm.
So please utilize that function. The other thing, of course, is if you want to do it.
Oh, the disclaimer?
Yeah.
Is that what you're talking about?
That's what I'm talking about.
So it's just us. We're not speaking, we're not authorized spokespersons for the University of North Dakota, or the Department of Physics and Astrophysics, or the College of Arts and Sciences. So the opinions expressed are those of myself and Wayne. It's just us, folks.
We don't even have
We're winging it. We just don't even have a script. So.
We don't even have a union card,
No, we don't.
So we don't have none of that. So we don't have permission to do anything except... Anyways, just to kind of let people realize about the schedule, heads up. So next week is obviously Veterans Day, at least for the United States, Remembrance Day for Canada.
Right.
And the university's closed that day. And to honor our veterans, of course, we will not be doing a podcast.
Well, we'd probably get in trouble if we came in here and did the podcast anyway.
Especially if we came here and got hurt.
Right.
Then the insurance probably wouldn't cover us.
It probably wouldn't.
Because you shouldn't be here when the university's closed. I'm sure that's what we would
I'm sure that's what we would
And you
hear.
can't blame them because we shouldn't be here when the university's closed.
Right.
And so, anyway, unless you're like essential employee.
Right. And then you better be here.
Is this essential, Robert, doing the podcast?
I don't think so.
So. It'd fall in that category.
I don't think animals are going to die or anything like that if we're not here.
So then we have to wait 2 more weeks before we do another podcast.
Right.
Maybe there's some like really cool stuff will happen between now and 2 weeks from now that we can report on.
Heck yeah.
Like
I
Beetlejuice
like
goes supernova or something dramatic.
Oh, that would be cool.
Wouldn't that be awesome?
We can hope.
Or Comet 3, I'm going to say it, Comet 3I Atlas goes in reverse and goes along the exact path that it was inbound.
You see, that would be so awesome. People are getting mad at us because we're saying it's just a comet, but you don't know. You're missing the point. We would think that would be awesome. I'd happily eat that plate of crow because, holy crap.
Can I cook that for you?
Sure.
I know I've seen some roadkill on the way in this morning. I can put that on a plate. Does it really have to be crow? It can be just roadkill.
I think it should be crow.
And can I watch you eat it?
Yeah, sure.
I think you might just toss it in the garbage when no one's looking. You see?
Yeah, right.
I want to make sure. You don't eat the feathers, right? You take
No,
them out.
no. You take them out, you fry it up.
You can use them for making pens out of later.
Uh-huh. Yeah.
Okay, and also just to remind people that we do upload our podcast the next day on Spotify. So if you'd rather wait until then to see the show, or better yet, watch it twice.
Hey.
You can watch
I
it
like
more
that.
than once because you miss the little things here and there, and then you watch it again, and you pick those little missing details up that otherwise, maybe some subtle jokes, you finally get the punchline.
Right.
Because most of our jokes are terrible. But anyways, speaking
for
for
yourself.
myself, I
My
am.
jokes
I
are
am.
gold.
I am. Okay, Robert, how do you want to start this?
Well, shall we start with?
Comets.
Comets. We
Comets.
have a lot of comets lately.
Did you notice that?
Yeah, I did.
There's like 4 comets that are up in the sky all at the same time.
To me, I wish it was like that comet in the 90s. I forget which one that was.
Hale-Bopp or Akitaki?
One of those two that was just like filled the sky.
Yakitaki.
Okay.
Yeah.
Because, we got out of class and everything to go see it.
I always remember that. That so far has been the #1 comet I've ever observed. Or literally you go outside and like lay down in a field and look up and it's stretched almost from horizon to horizon.
Right.
That was way better than Comet Halley. I remember Comet Halley in '86.
It was a spot in the sky.
In February. It was right low, at least from
Yeah.
where I was observing from Nova Scotia. It was right low in the horizon. It was cold because it was February. I was looking at it. And you had all this sort of, it's going to be a great thing, this build-up, to Comet Halley. And then when oh, my God. Maybe, once again, you had to be in the southern hemisphere to have a decent look at it.
Right.
So it's one of those cases, well, it depends where you are on the Earth, whether you got a nice
Spectacular view or not.
Yeah. So comets, you never know what you're going to get. So this comet is actually, and the name of it is 2025 K1 Atlas. So there are a lot
So
of
it's-
Atlas comets.
It's the
around.
same group that found
Yes.
3IA that
Right.
found this one.
Now, this comet went the closest point to the sun, what we call perihelion, way back on the first part of October, on October the 8th. And it was expected because it came within only 0.33 astronomical units. And for those who don't remember or never heard us talk about this before, an astronomical unit is the average distance between the sun and the Earth.
Mm-hmm.
So in miles, that's what, 93 million
93
miles?
million miles.
Approximately. So it's like 146
Something, yeah.
million kilometers roughly. Anyways, it got fairly close to the sun, and they thought that it would break up. You know, a lot of times comets are like loosely packed. You know, some descriptive words we've used in the past were like dirty snowballs.
Yeah.
But even then, you could take a snowball, if you're familiar with that, and you compact it really tight. So it's hard to break it apart. But we're talking about really loose type of almost like cotton candy in some
We're talking
sense,
about it
right?
getting really close to the sun. That's closer than Mercury, if I'm not mistaken.
Yeah, and so in that sense, everyone expected that this object would break up, and that's not what happened. Its tensile strength, in some sense, right, was strong enough that it survived the close passage of the sun. But what makes this comet interesting is the color. Notice you don't see a lot of green in that image.
Right.
In fact, it's being referred to as the golden comet. Not that it has gold on board, which would be nice, especially if we were able to get some of it.
Suggests a lot of silicate dust.
Yeah. You know, some people suggested that we could capture some object and let's say, you know, like mine the heck out of it. Think of an asteroid that contains like some rare elements or something, and we make a fortune. But the problem is, if you brought all of that material to Earth, I always thought about this, right? You have in the distant future, right? You have the technology to bring in some asteroid in Earth orbit, and you mine it for its rare elements.
They're not rare anymore.
No, that's right. You'd have to bring it back just a little bit at a time in order to get like a decent amount of money out of it. Because if you brought the whole thing back, there are literally millions of metric tons of material that just shows up on the market. And so the price just collapsed overnight.
Right.
And it's not worth anything.
Yep.
So if you think of it in that terms, it may take a long time to see your profits out of something like that. So the comet, yeah, it's not made up of gold. It's golden in color. And that's because it lacks carbon compared to a lot of the other comets that we've seen.
So it doesn't have that cyan.
It doesn't have the cyan. Yeah, very low abundance. So if you remember the podcast last time, we had Dean Smith here talking about Comet Swan. And it's like a gold diffuse blob of light ahead of the coma part of the comet itself. Yeah. And that's due to CN type of emission. Right?
That'll make it glow blue-green.
Yeah.
And
then the carbon on top of that, right, will give you the greenish, nice color. And this one doesn't really have a little bit of green you can see there, but it's a lot of gold for sure.
Yeah.
And it's underabundance in carbon, you know, and that comes from spectroscopy, right? We do those type of precise measurements.
Like I said, I figure that probably means it's got a lot of silicate and a lot of just dust, so probably some magnesium and iron in there too.
And what it really means, of course, is that their comets don't all come in one flavor in that sense.
Right.
You can have a whole range of properties of comets. So then you get something coming in inbound from outside the solar system, and it's a little different than the average of comet. Big deal. We expect that anyways, right? There's a wide dispersion in the properties of
in the
these
comets
objects.
from our solar system.
Yeah, so why we would expect something coming from another star system to be exactly like the comets we have in our solar system, and there's no exact comet anyways, right?
Right.
So, yeah, so that's always funny why people get all hyped up, amped up over stuff like that. But, hey, the other advantages you can think of is as long as people get interested in science,
let them come. Huh?
you know, then
Just
let's look at all these
listen
things,
and
right?
let's talk about what we do know, you know.
Yeah, kind of thing.
Speculate, but
Yeah. Now, if you want to find this particular comet, what I've done is actually take a finding chart for tomorrow, because there's no sense of putting one here for like this morning because we're past that, right?
And comets are usually fast moving.
They are. And so if you are watching this podcast live, as instead of being dead, I guess, then you wouldn't be able to watch it. But if you're watching it as we're streaming it, or you watch it sometime tonight, then tomorrow morning, get yourself out there, you know, just before sunrise and look towards the east. And you will see then this comet. If you have a telescope or a nice, decent pair of binoculars, and especially if you're in a dark site away from the city lights. And notice that the comet is essentially in the constellation of
Leo,
which is my horoscope, my birth sign.
Oh, really? Okay.
So there's a cosmic connection here. You see?
I won't say where it would be due to its position, what pops into
Well,
my
I'm
head.
just
But
thinking like tomorrow's Wednesday, and
Yeah.
that's the draw of the Powerball. So does this imply that I should run out and get a ticket for tomorrow night's draw?
I don't know. I don't know, man.
You know, Robert, if I do that and win, I will split it with you.
Okay.
But of course, I'm not talking 50-50 split.
Absolutely. No, you're not. I wouldn't either.
I'm just saying I'm giving you a little bit of money here
Yeah.
to put a smile on your face. How's that? Anyways,
works.
so yeah, if you get out there before sunrise, you'll be able to spot the comet. And the other thing, if you get out there before sunrise, looking sort of above and to the right of Venus, you'll see Comet 3I Atlas.
Oh,
It's in
so
that
that's where it
general
is. So it's
vicinity,
over there
yeah.
near Spica.
Yeah, so it's getting to the point now where these large telescopes will soon be able to, look at it. Certain amateur telescopes
Right.
certainly can do that. Larger telescopes, you're scared of looking near where the sun is for obvious reasons.
Why?
Yeah, you don't want to swamp your detectors
I mean-
and all this stuff and accidentally, do
Start
some damage
damaging
to those.
stuff.
You have to be very careful anyways. Yeah. Okay, Robert, so what else is in the news lately?
Well, we've got another launch. This
We do.
one by Blue Origin.
This is your favorite company.
I-
You like this company,
I
don't
like
you?
this company because I would like to see there being competition. I want to see 3, 4, 5 big launch companies and dozens of light launch companies. So Blue Origin getting in there and going tickles me pink. I wish Boeing hadn't messed up. But it should be more than just SpaceX. Is all I'm saying.
Well,
And
I mean, the Blue Origin has undergone a lot of
change.
delay and a lot of delay.
Yeah.
I mean, their initial plans were to launch a lot of these rockets like many, 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 many years ago.
Yeah.
And
Well,
Jeff
this-
Bezos, of course, been concentrating on those suborbital launches.
Yep.
And those have been very successful.
Yep.
And there's, as far as I know, there's been many launches. I don't remember the exact number anymore. And none of them had any issues. Well, there was an issue with an unmanned one, right, where they had a payload and there was a rocket malfunction that they had to
I
correct.
was
But
about to
nobody
say,
was.
they were having problems with their big engines blowing up.
Nobody was on board that rocket. But so this is the next step. Now, we did have a launch of New Glenn. This must be almost a year ago. That was very successful. This time we're getting ready to launch because we want to send a General Motors car to Mars. The Escapade. Did you notice that?
I hadn't noticed that, but now that you mention it, now I get it. Yeah.
So what is the Escapade? Clearly, well, I shouldn't say that they're not because there's some other space company that launched a car into orbit around the sun. You remember that?
I do.
That was the Falcon Heavy, and that was the Elon Musk's, what was a Tesla that he
Tesla.
sent up, right? A
Yep.
red Tesla. And that's still up there orbiting the sun.
Yep.
Be interesting to know what that would look like after, being in space for like
Well, the
20 or 30 years.
paint's going to fade because of the ultraviolet and X-ray.
And it's going to be dinged by
bombardment. It's
micrometeorites.
going to be dinged.
And those are fastly moving, so there'll be like little
Holes.
holes, yeah,
Yeah.
also like ball bearings or something like buckshot hitting the car, right?
Right.
So it'd be kind of cool though to see. I don't think they have any sensors on board. That would have been interesting if they would have kept.
You see, that was my whole point about it. It was a publicity stunt. Do something interesting with it. Sure, make publicity, but do something interesting.
Like a camera that runs under solar power.
Right.
So when we came near the sun, the camera would have enough power to come on, and we'd have live views from the Tesla
From the
roaster or whatever it is.
Tesla
Right?
Spacer.
Yeah. That would be kind of cool, right?
But I also agree with our viewer, Jeff Weiss, that it's more space junk.
Yeah,
in the end.
definitely.
And we've got too many satellites. I go out to the observatory right now, and if I see, for any 20-minute span looking at the sky, if I don't see at least 3 satellites go across my field of view, I'm like, whoa, holy cow.
Well,
So-
but somebody's junk is someone else's treasure. If you went out, if you were a private space company, Robert,
Yeah.
and I guess legally you can do this, I don't know, and you go out and you actually capture that car and brought it back to Earth, I bet you could sell it and make a lot of money.
Yep. And the answer is no, legally you can't.
That's owned by SpaceX,
Yep.
Elon Musk, right?
You got it.
So we'd have to have his permission to do
That's
that.
one of the questions about doing, as is suggested, the space cleanup is the legalities of, who gets to clean this up? Who needs to clean this up? Because a lot of it is government-owned materials.
Now you were talking
and
about
so forth.
you were talking about the satellites, and you can see, and you can see simultaneously almost any time you look, you'll see satellites if you look careful enough. That I've seen a lot of the images taken of comets, for example, like Comet Lemon recently, and a lot of those wide field angle images, they're coated with multiple satellite tracks. So if you see one that doesn't have it, that's because it's been heavily processed to get rid of those satellite trails. But yeah, any long exposure with a wide enough field of view, you're going to pick up all kinds of them, right? And we can't get rid of them. I mean, they're up there, they'll gradually come back, but it's like, what authority do we have to say, hey, you're polluting the night sky on us, you're ruining the sky in that sense? They don't care.
They don't care.
Because they're there for profit. They're making money.
Right.
And the government goes right with it because they make money as well, right? You know, it's all, it is sad.
It is sad.
Yeah.
But, you know, until the nations of the earth get together and decide some legalities of space salvage, there's nothing we can do.
Okay, so here's a question for you. You said I can't go up in a private company and grab the Tesla vehicle and bring it back and sell it and make all the money as my money, right?
Right.
What happens if a satellite from a company like SpaceX or any other company for that matter crashes in my backyard and destroys a valuable property item that I have, like a building with a bunch of equipment in it that's worth a lot of money? Who pays for that then?
Hope you got good insurance.
Is that an act of God?
It's certainly not covered under your standard policy.
Well,
I'll tell you that.
why isn't the company who put it up there responsible for that?
See, that's the good question. And it needs to be answered, especially with more of these things going up.
Is there any lawyers out there that can listen to this podcast and think about those type of questions?
That would be nice.
Because usually
answers to that.
Usually a lot of this stuff doesn't get solved until it actually happens, right? Or you're out in your backyard and a piece hits you on the foot, right? And you got to go get medical stuff done to you. Well, who pays for that if you didn't have medical insurance? And you're out like $10,000 for some medical procedure.
And the answer is yeah, but the likelihood of this happening. But the thing is with more and more of it being up there, it becomes more and more likely that it's going to happen.
Yeah, I mean, there are people that are reporting, you know, stuff falling in their backyards and stuff, or in open fields in different countries around the world, and they end up to be different tanks and pieces of equipment from rocket from different stages and stuff, right? So if you're going to launch more and more and more and more of this stuff over time, then clearly this could be an issue in the future. It's interesting from a legal point of view.
It is.
In other words, can you sue these companies? That's what I'm after, right?
And that's the big question. And nobody's brought it to task just yet.
Yeah.
And, you know, the companies are, of course, saying, hey, we can't control where these things are going to land. Why should we be responsible?
Yeah.
And to a degree, they're right. But in the end, these are things we need to start questioning. And I think, yes, it should be the company's problem. And that would hopefully slow them down and make them think a lot more about how much and what they're putting up there, because that increases their liability.
And Jeff once again mentions the fact that in a couple of years could be over 100,000 satellites. And yeah, that, you know, no pun intended, but that's an astronomical number of satellites that's going to be put in space. And it's not just one country. That's the thing, right? One country has their system, but other countries are not going to trust that. Oh, you can use our satellite system. Yeah, until there's a war or hostilities break out, then you shut me down. Right. That's why some countries, you know, as we hear, are not too happy about buying F-35s from the United States, because they always fear that there's a backdoor sort of software thing that can be turned on in case some hostilities break out, like us.
And we can shut down their plane.
And they can shut down. So, like, you could think like Denmark buys a bunch of F-35s to protect Greenland, and the United States, you know, attacks Greenland. Well, the United States just shuts down all those F-35s that were purchased from them, right?
Right.
You know, you always worry. So then,
concern.
Yeah, and so then other countries are going to have their own satellite system.
Right.
To make sure in bad times that they can run their equipment and do what they need to do. Then you're up to 100,000, 200,000, 300,000 of this stuff in orbit. And at what point does it become unsafe to even launch a human being to the moon, because you got to pass through essentially a debris field of trash cans trying to get to the moon space, you see? Mm-hmm. And then the chance of a collision goes up to becomes a value where it's like it's really a finite chance that's pretty large.
Right. I mean, it's gone from being an infinitesimal amount chance to now it's, a non-negligible
And
amount.
what happens if we ever get into this position where these things start running into each other and you got debris, satellite
got
debris spread
Crap
all over?
collision debris. You've
Yeah.
got China and the U.S. testing out their anti-satellite
And that's
missile
happened in the
systems.
past. I mean, it's not,
And
never happened.
This is yet more debris and more garbage that nobody is willing to sit down and negotiate.
Yeah.
How do we get rid of it?
Remember the movie Gravity?
Yeah.
I mean, that's what that was based on the premise, right? You're going
Yep.
to have this collision that you can't avoid, and you never know what you end up with, right? So it can be a real mess if we're not careful.
Absolutely.
And of course, yeah.
Jeff is making some really good points. In the end, we will lose our GPS
Yeah.
communications when these things start colliding.
Yeah, for sure.
Yeah.
Yeah, it'll be a really hostile environment for a while, and some of this stuff is in high orbit.
So it's
It's going to take tens of thousands of years for some of that stuff potentially to rain back out of the orbit,
to
right?
put it in perspective, it is like radioactive waste.
Yeah, in that sense it is.
like the current nuclear power waste.
So imagine, like 75 years from now, like the people are just cursing our generation.
Yeah.
As we started down this role of doing this, right? This long road of putting all this stuff in space and ruining the environment for future generations.
Absolutely.
In fact, you could argue light pollution does the same, right? We're mainly an astronomy type of podcast. How many times do you go outside and can't see something because of the lights of the city? And people put up more and more outside lights, right?
I'm worried about that for obvious reasons, but I'm also less concerned about that because 80% of the population lives in of the U.S. anyway, lives in urban centers now, so they're not going to see anything anyway. But out here in the middle of nowhere, why can't you turn off some of these lights?
Especially the ones that are pointed straight up.
Right.
All you need is to fly like an aircraft, like a drone, taking images at night to see where all the lights are pointing up. And what's the point of that? To stop
Right.
people from robbing your car lot or coming in on balloons or something? What's the point of it? Really, when you think
You're
about it,
right.
right?
Absolutely.
You want the light down on the ground to be able to, have a camera that's running, I guess, to be able to see the parking lot.
And you can put motion detectors on them so they come on when
Yeah.
people are around.
Yeah,
You
it's just
know?
amazing. You hear stories about how fantastic the views were back several hundred years
Yeah.
of the night sky from almost anywhere. And this is related to how, like, ancient cultures have a lot of astronomical related things deeply ingrained in their, not only their religion, but also their philosophy and so on, their societies in general. Because you put yourself back in ancient Egyptian time, thousands of years ago, looking up at the night sky on a nice clear night. Imagine what you could see compared to what you'd see now
Right.
from most areas, right? Huge difference, huge difference.
Yeah. But people still navigate about it. You could tell where a city was, and you can nowadays, except they're everywhere. But you used to be able to see the horizon glow where a city was,
Yeah,
even when it was just lit by oil lamps and candles.
yeah.
So
I guess the place to be nowadays would be what, in the middle of the Atlantic Ocean?
something like that, or the Pacific.
And you'd never have to worry about the city lights then, but you
Yeah.
just have to worry about lights from passing container ships or something. And
Right.
if you're off the beaten trail, or most of these ships follow, then of course, but then you're into this unstable platform that's bobbing around on the
Bobbing
waves.
around. Yeah.
And then you got to worry about actively pointing your telescope to some source very steadily. And that becomes the problem. Unless you're on a deserted islands. We need to go to Gilligan's Island,
Right.
right, and set up a telescope. Can we do that?
I don't know.
What was that, a 5-hour cruise, or how'd that go?
3-hour tour.
3-hour tour. We can do if only there was one about 3 hours away.
Right.
Maybe by plane, but not by boat, I'm sure. Anyways.
Yep.
Yeah. And that's exactly, a small person has no voice. Yeah,
Right.
we have a voice, it's just no one can hear it. No one wants to hear it.
Nobody wants to hear it.
That's a real problem. So
It
we'll,
is.
we'll see where all this comes to a head. So anyway, so the New Glenn vehicle, as we talked about, is going to launch two NASA probes, the ESCAPE probes, the Escapade probes, sorry,
Okay.
that are going to Mars. And hopefully the soonest that they can launch, I understand, is November the 9th. I don't know if that has changed in the last day or so. And these probes are they're really, in some sense, they're test objects for the rocket.
Okay.
Do you really want to put a $10
I
billion
hadn't heard
space?
about these, so I didn't.
Yeah, do you want to put a $10 billion space telescope on board New Glenn and launch it?
No.
Where it's only had one successful flight,
No.
one test? No. And so you have put something on board where you can afford to lose them in case of,
Right,
the
right.
rocket doesn't make it. So yeah, these are designed to study like the magnetic field of Mars and so on. So
Okay.
the atmosphere of Mars from orbit. So they're going to go into Martian orbit, and that's it, Mars orbit. So we'll see how this plays out. So hopefully it's successful. Like you said, more competition, the better.
Absolutely.
And we'll see, what happens in the future for this kind of stuff. Now, on to the next item.
Woo.
This is actually a quite interesting study that was done recently by a group that was trying to measure, at least part of what they can do with their observation is to measure the temperature of the universe. And back in the past, roughly about 7.3 billion years ago. Now, in astronomy, when we talk about distances, we measure things in terms of the redshifting of the light.
Right.
In this case, it's at a redshift of 0.89. Now, that means you're looking back to an earlier time in our universe. In this case, with the standard cosmology, the concordance model, as we call it, a redshift of 0.89 works out to you're looking back about 7.3 billion years.
Okay.
Now, the universe itself is about 13.8 billion years old. So, in some sense, you're looking back a little bit more than half the age of the universe.
Okay.
Now, we know that if we go back in time, the universe will be hotter.
Right.
Now, there's not an argument there, and people try to make that argument, but they're just being silly. I mean, these are observations, direct measurements. Being silly as in there will be people that argue the Earth is flat and so on and so forth.
Right.
That's what I mean by being silly. Now, as you go back in time, then you're getting to a hotter, denser phase to the universe. So today, the temperature around us now is on the order of about 2.7 degrees Kelvin, or 2.7 Kelvin, as we would
Right.
say. And what this study did is try to measure what was the background temperature that at this high redshift of 0.89. And 0.89 is not a high redshift.
No.
We've
got
James Webb have
16.
looked. Yeah, redshift of 16, over 13 billion light years away. So looking back over 13 billion years in the history of the universe is not unusual nowadays. We
Right.
have that. But what this study did is it was able then, based on molecules, and these are observations from ALMA, looking at molecules, and in particular the HCN molecule, to see what kind of a bath, an ambient temperature bath that these molecules are found in. And this ambient temperature bath means that the molecules are in this excited, this higher energy state
Right.
than what they would be if they were in a temperature of 0 Kelvin, absolute zero. That would be like the minimum temperature they would have, or minimum energy state they would be in that sense. And so by looking at the spectrum of these molecules with the ALMA telescope array, they were able to determine that the temperature that these molecules find themselves in is on the order, and you can see there in the abstract, about 5.13 plus or minus 0.06 Kelvin. So that is higher than the 2.7 Kelvin around us locally today, because you're looking back into a warmer era or epoch of the universe. Now, as you go back in time, the temperature goes up. It's not a linear relationship. In other words, if you go back to half the age of the universe, does the temperature double? No, it's not type of relationship. So as you get closer and closer and closer to the beginning of the universe, the temperature starts blowing up hugely in size, until essentially, as you get to the very beginning of the universe at t equals 0, classically the temperature is at infinity.
Right. Quantum mechanically, not so
something
much.
else. And actual reality, we don't know.
We don't know.
Because we don't know what the conditions of the universe were like at the moment that it was formed at t equals 0.
That's something that it is good to point out, in my opinion, is that there is a point at which we have to throw up our hands because the laws of physics break down at those temperatures and those densities and those times. So, we don't know, and anybody claiming they do is speculating.
Yeah, being foolish, is the term that I used, right? In that sense. But yeah, and this is not unusual. I mean, the leftover heat from the Big Bang, which was initially seen back in 1964, and then ultimately Penzias and Wilson won the Nobel Prize in Physics, and I think it was in the 70s or so, for the discovery.
Usually it's about 10 years after.
Yeah, for the discovery of the leftover heat from the Big Bang. This was actually seen, it was actually a famous Canadian astrophysicist that was looking at different molecules and stellar spectra, so looking at sort of the interstellar matter that's in the way,
Yeah.
and realized that these molecules displayed spectral lines that was consistent with them being in a heat bath of a temperature of around 3 Kelvin or so. And it was the CMB, and no one realized it, at the time. When Penzias and Wilson made their observation.
So somebody else actually discovered it and mentioned it, but nobody realized what it was.
Yeah, didn't know the significance of it.
Right.
And but the time when Penzias and Wilson announced their observation, there was theoretical work that was done at the same time by Robert Dickey at Harvard University and others who could explain right away. In fact, was explained in the same journal.
Right.
Right. That the article of the observations of the CMB were made at the same time, and actually explain to people what the significance of this observation is, that it's consistent with the leftover heat from the Big Bang. So as you go back in time, the universe gets denser and hotter, and denser and hotter and denser and hotter. Is that actually what occurs? You always want to test these ideas.
Right.
So this paper is testing that type of idea. So, for example, as you go back to higher redshifts, you go back in time, we expect the leftover heat from the Big Bang, as we mentioned already, the temperature to increase. Now, this is not the first kind of test of this. People are testing this as much as they can when the situation arises. It's just one more data point, if you like to add. Now, what's good about here is that they have a very precise measurement of the temperature, one of the most precise measurements that have been done because of the way the temperature affects the appearance of the spectra of these molecules. You can use them as a very precise diagnostic tool to estimate the temperature of the environment that they find themselves in.
Right.
So that's why it's extremely important this time around. The plot that you see here then shows on the vertical axis the CMB temperature, and CMB, by the way, stands for cosmic microwave background. And why we call it that is because today the leftover heat, because of the expansion of the universe, has cooled down to a point where the peak of the emission is at about 1 millimeter.
Okay.
And that's picked up it's in the microwave region of the electromagnetic spectrum. So we call it the cosmic microwave background because of that.
Right.
As you go back in time, that peak shifts to shorter and shorter wavelength. So there was a time in the past where the peak was in the optical. So with your eyes, you could see
You would not want to be in that universe.
So with your eyes, you could see all that background radiation from the universe. And if you go even earlier than that, it's shorter and shorter. And then it's in the very shortly after, it's in the gamma rays. You don't want to be in that heat bath either, right?
Right. Well, I was just pointing out to have a peak in the optical, you're about 6,000, 7,000 Kelvin. So imagine everywhere in the universe being at 6,000, the temperature of the surface of the sun.
Yeah, exactly. Not a good place to be.
Yeah.
So we can test then how the temperature of the cosmic microwave background should change as a function of time since the Big Bang. And that's what this plot is showing you. The thing to note here, the result from this paper is the red symbol that you see plotted there, sort of, less than a redshift of 1. The redshift is given on the horizontal scale on the bottom. But a lot of the data points, and they have their uncertainties that go with them, some of them are fairly large. And there's one measurement way out at a redshift of 6, and look how large the error bars are.
And I was going to talk about that in a minute.
Yeah. So that we can't really constrain then the temperature of the CMB to the point that we want it, right? To the value we like to have, a nice precise measurement. We can't really do that with that error bar. Hopefully in the future these errors will go, be a lot smaller, the uncertainties in the measurement. But the one for this paper is very, very precise and gives us a nice, interesting data point there at close to a redshift of 1. And what it shows is, yes, the measurement of the CMB that we get at that redshift is consistent with the standard Big Bang model. There's no weird stuff going on. There's no sort of huge peak in the temperature caused by the release of some energy from some known forces or any of this kind of stuff, right? It's totally consistent with the standard sort of Big Bang theory that we have today. And always remember, it's a Big Bang theory. And the word theory in science means there has to be supporting evidence. It's not just a hypothesis.
It's not just a guess.
It's not an idea or anything like that. There has to be something there. And you might ask, what is the supporting evidence then for the Big Bang theory? And the 4 major pillars of support for the Big Bang theory is, number 1, nearly 100 years ago, we discovered that the universe is in a state of expansion. That was in 1929 by Edwin Hubble, for example. Number two, well, in 64, we discovered the leftover heat from the Big Bang, which showed that the early universe was very hot and very dense. Okay? The next one is when we look back in time, and we can do that because a telescope, I like to say, is a time machine.
Right.
But it only works one way. You can only see back in time. You can't see forward in time. And so when we look at distant objects, because of the finite speed of light, we look back in time. In fact, our eyes are a time machine. When I look at Robert, I don't see Robert now, immediately in the present. I see him in the past several nanoseconds ago, because it takes time for light to reflect off his surface and enter my eyeballs.
And even then, it's going to take a few microseconds for your brain to process the
Right.
images.
When
So-
I go out at night, like say tonight, and look at the moon, I'm not seeing the moon as it is right now. I'm seeing as it was about a second ago.
Right.
When I look at the sun, if I go outside and can see the sun today, I'm seeing the sun as it was a little over 8 minutes ago. So because of that finite speed of light, anything that's far away, you see them as they were, not as they are.
Right.
So in this case, then, when you look at the very early universe, let's say you're looking at objects that are 13 billion light years away, that's with a B. You're seeing them as they were 13 billion years ago, long before the Earth even came around. In fact, about 9 billion years before the Earth existed.
I've recently watched a guy talking about this, and he put it in an interesting way. You're looking back in time, so people go, well, how can it be backwards in time in all directions? And the root of the answer is because that path from here to there no longer exists. Time is not linear, for one, and number two, the path is moving outward, but the view of the path is moving inward. So that view we're seeing does not exist anymore.
And the other way I would look at it is, doesn't matter what direction you look in space, you're looking over some finite distance.
Right.
And it takes light time to cover that distance.
There you go.
So everywhere you look, you're looking into the past.
You got
Now,
it.
the thing is, when we look into the past in our universe, we find that the universe does not look the same as it does around us locally. So the galaxies look different. There's a lot smaller galaxies, a lot more merging that's going on, higher fraction of active galactic nuclei, as we call them, and so on. So galaxies evolve. That is consistent with the Big Bang theory.
So that's the third pillar, right?
The fourth pillar is, where the heck does the hydrogen come from in our universe? The first generation of stars convert hydrogen to helium. And then other generations, they will convert helium into carbon and oxygen. And if they're massive, they'll blow up the supernova and go all this different process. Now you get the iron, and in the explosion of iron, you create all these other heavier elements. You can fill up the periodic table and blah, 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 blah. But where did the first generation of stars come from if somehow hydrogen had to already have existed?
Right.
If there's no hydrogen, there's no stars.
And when you look, there's hydrogen everywhere and about in the proportions that you would expect.
So when you take the known laws of physics and apply it to the conditions of the very early universe, in which we have high confidence they're valid,
Right.
we're not talking at t equals 0,
Right.
all right? What we find is that there is enough time, even though the universe is rapidly expanding, so we need a few minutes, okay, 3 minutes or so, there's enough time and enough energy around, that is, it's hot enough that you can actually make hydrogen.
Shouldn't that have, this is something, thank you for bringing this up. Shouldn't that have actually cooled the universe dramatically at that point too? The condensation of hydrogen out?
Well, to a degree, but hydrogen is, and the universe should say, is rapidly expanding. So most of the cooling is the fact that heat got to fill up an ever
Fair,
larger
fair.
volume of the
So
universe
it would be
itself.
a little dip in a big
right.
spread.
And yes, that's right.
Okay.
And so, there's enough time to form some helium. So by mass, you form roughly 74% hydrogen. Roughly 25% is helium. And that's it. You can't form other stuff. Why? Because the universe cools too rapidly.
Right.
It's like, way of thinking about it is preheat your oven because you're going to cook a 16-inch pepperoni pizza. Yum, yum. It's almost close to supper time.
Oh, my.
And I'm feeling hungry right now. And you get the oven to preheat so the buzzer goes off that it's at the right temperature to cook your pizza. You put your pizza in the oven, and then you turn the oven off. Or the power goes out at that point, and it's an electric oven. And then you wonder, is there enough time, given the fact that the oven is cooling down, is there enough energy available, if you like, right? The temperature's high enough that by the time the oven reaches ambient temperature, local room temperature, that it was enough to cook that pizza so I can eat it. And for the case of hydrogen and helium, there is enough time to cook some amount of hydrogen and some amount of helium, but not all the other stuff.
Yeah, and a tweak of lithium, beryllium.
Yeah, there's
boron.
a minor amount of lithium for people with memory issues,
Yeah.
boron
Tweak.
and beryllium, but they're a really, really small concentration and essentially negligible in that sense.
The neat thing is that I'll mention this too. In the first generation of stars, any of that would have been cooked into heavier elements because it makes those elements fuse readily compared to hydrogen or helium.
Now, if the early universe was not hot and dense, there's no way to make the hydrogen. For example, you think of we always like to think of alternative ideas. There is there is the steady state model that actually dominated, cosmology especially back in the 50s and part of the early 60s before the CMB was discovered. And that model essentially boils down to, you look at the universe around us today. That universe that you see on average is the same as we had for all of time and always will be the same going off to infinity in the future. So you don't have to worry about what is the Big Bang, what banged, why did it bang, what happened before the bang. All these questions are meaningless in the steady state model because the universe is the way it always been and it's been there for eternity. So we don't need to explain the origin of the universe. It just has always been here. That's how you kind of get around
Except
it.
That's not really an explanation.
Now, then you start making observations, and at some point you run into observations that turn out to be inconsistent with the model. And a good one is that, wait a minute, the universe is not static and unchanging, it's expanding. And now, like I said, that's about 100 years ago that we figured that out. So then you go to the people who support the steady state model, notice I call it a model, not a theory, and they go to steady state modelers, if you want to use that term, and say, well, then what do you make of this expansion idea that we see the universe is expanding, and it's not just Edwin Hubble that sees it. Anybody with a decent telescope can see it.
Right.
You can't hide the fact.
You can't hide it.
Right? So what do you do there? Well, they said, okay, as the universe expands, new matter is created to fill in that void. So then on average, the density of the matter remains the same for all of time.
Except that's not what we see.
Well, it's not just that. It's like, okay, what is the process that creates this new matter out of nothing? Well, we don't really know. We'll figure that out in the future, later on. That's next generation will figure that out, hopefully. That's essentially what was done, more or less.
Right.
Now, when the CMB was discovered in 1964, there is no hot, dense phase to the universe if the steady state model is correct.
Right.
That was the end of the steady state model. That fell apart, you see.
Well,
so there
were some old guys that hang on to it for another decade or two. But
right. But I'm sure there were some old guys after the 1930 stock market crash hold on to those paper stocks too, thinking that somehow they would magically come back again and never did.
Yeah.
So there's always people who are like that, of course. And it's hard. We're humans, right? It's not like we're robots. I mean, you throw a switch and we change our opinion. They're always hanging on to this.
As I heard it put one time, you're talking about guys who've hung their career, 20 or 30 years of their work and their life depends on this being the case, this being true. They're going to fight tooth and toenail that they haven't wasted their time.
Well, in science, the way it should work is that if observational evidence or experimental results come along that show that your idea that you've hung on to for 20 or 30 years or worked on is actually totally wrong, it doesn't just need a minor modification.
Right.
Then as a good scientist, move on.
Move on.
And that's the way it should work.
Most do.
But we're human. We are human.
Always have these guys.
We are human, and we have to always factor that in.
Yeah.
Okay. Anyway, so far so good with the Big Bang model in this case, the way it's being tested. But we'll see how.
I'm going to mention one of these things too that I find interesting is that the error bars get larger the higher the Z number, and you get points that move off of that model a lot more frequently as you move to higher and higher Z. So the further back you're looking, the more uncertain things become.
Yeah, you can just think of it as scatter, right? So you're scattering around. You're not going to stay on that line, right? You're going to be above and below the line. And if you have enough scattered points, on average, hopefully they equal where the line is.
They equal where the line is.
Yeah, and that's just because Those measurements are higher redshift. The objects are a lot fainter.
Yep.
So your signal to noise is a lot lower, which means it's harder to get a really good measurement unless you have a lot larger telescope or more sensitive instrument, which will happen in the future. I mean, James Webb had shown that, for example.
Absolutely.
What you can do with a larger telescope compared to the Hubble Space Telescope.
Right.
So that proves the point on that issue.
I think we're about at the limit of what we could do with the detectors, though. Is that?
Well,
Unless
I mean,
we discover
there's
new
still
physics.
well, there's still an era, after the universe cooled down, the structure formed, and before we see the first, generation of galaxies form. That's kind of the dark ages.
Yeah.
So we're definitely trying to explore that region, and that may be using like hydrogen. I mean, people use the 21 centimeter line to observe, the cosmological hydrogen that's out there that would be floating around in the space between galaxies and extragalactic or intergalactic space. And that can tell you a lot of kind of interesting information.
I mean, it's neat stuff. It's,
Yeah.
there's more Nobel Prizes out there to win, folks.
Well, I mean, there's a lot of ideas that people will come up with. We don't even know what they are because
Right.
people are, a person's brain is really, awesome when you think about it. Yeah, we got AI and all this other stuff, but, humans can really come up with some really decent things when you think about it, right?
Yep.
No pun intended there.
There you go.
Anyways.
So moving on.
Moving on. So this is a nice study. This is, you might remember recently, Chang'e 6 was the rover that landed on the far side of the moon. Not the dark side of the moon. The far side of the moon or the back side of the moon.
The sun lights it up once every month. So.
Yeah, so you get just as much sunlight on the back side as you do on the front side. So there is no dark side to the moon from that point of view. Now, one of the things it did, it was the first rover to be on the far side of the moon, gathering up material and bringing it back to the Earth. So we'll credit China for this, of course. And we note that, images that were taken in the era or the dawn of the space age when we had spacecraft that which is I think the Soviet Union was the first spacecraft that went behind the moon and took a picture of the far side. It was our first time to see it as human beings. It does not look the same as the near side of the moon.
It does not. It looks very different.
Very different. There are a lot less of Maria, or the seas as we call them on the moon, which is lava, ancient lava that spilled out onto the plains of the moon, billions and billions of years ago. And so for some reason, and we don't know exactly why that's the case, people are still researching into that even today, of why the far side of the moon looks completely different. And so it's interesting if you can go there, and unlike the Apollo program where we gathered material from the near side of the moon and brought it back to Earth, and also some other unmanned spacecraft have done that, including with the Soviet Union. We've never sampled the far side of the moon. This is the first time this has been done. And because of that, you're always wondering, well, what kind of things are we going to find? Is it going to be the same as the near side, or are things are going to be different? And what's that all about? And so in this paper that you see here that's been published recently, is they sampled some of these material that they brought back from the far side of the moon. And it turns out that there is some significant artifacts, some nuggets in the soil and the small minor rocks that they found that's consistent with what the moon was like, right? Very early on in its history. And very early on is on the order of like 3.92 billion years ago, back in the era of the late heavy bombardment, as we call it. And you can actually pick up remains of some of the colliding meteorites or even maybe asteroid sides stuff that came in and broke apart, right? And we're finding pieces of fragments of that material.
What I'm finding interesting from this significant section, which I've never heard of, is that a lot of it apparently is chondritic. And that's surprising to me because at that stage in the solar system, it should have been well processed. So a lot of it should have been achondrites.
In fact, if you go to the next slide, you'll see some of the slices of the material that was picked up. And you can see some of the geology here in these samples.
Olivine.
Yeah, it's showing you some of the structure, some of these fragments, really tiny fragments. You look at the scale there, 50 microns, 100 microns, and so on. So these are really zoomed in images of some of the pieces of the material that they brought back. Well, what it indicates, which I thought was interesting, is that these could possibly be, these meteorites or even asteroid-like objects, that they could possibly be a source of water. Both for the Earth and on the moon. Now, the moon's water could be locked in underground, right? It makes it very difficult to find.
Or it could be hydrated minerals.
Right, or anything on the surface would have, long since been disassociated by the ultraviolet light from the early sun, sort of thing, and long since gone or whatever. But could this actually be these type of objects in that period of late heavy bombardment? Could they have brought in a major source of our water to the Earth itself? And we're making a distinction here between cometary objects and meteorites or small asteroid type of objects that bombarded the surface of every object in the solar system.
Right.
I mean, that's one of the things that the space age told us, that if you go to Mercury, you look on Venus, we do with radar, you look at the surface of the moon, you look at places of the Earth, although it's affected by erosion and so on, tectonic plate activity. You look on Mars, you look on the satellites of Mars, Phobos and Deimos, you extend that out to the moons of Jupiter, the moons of Saturn. They are heavily cratered, a lot of these objects. So we know that very early on in the history of our solar system, it was a very hostile environment. I mean, you wouldn't want to be living then, right?
No.
Can you imagine the stuff raining in all the time at random times, right?
Be impressive meteor showers, but no thank you.
Yeah. I mean, just look at the surface of the moon and look at all the craters.
Right.
When we're first ramping up the human exploration of the moon, people often wonder, are those craters due to projectiles hitting the moon,
or
are
volcanoes?
Or volcanoes.
Yep.
And it turns out they are projectiles. There are some signs of some volcanoes, but very small in number.
Right.
So they are definitely, almost 100% due to incoming projectiles. And you wouldn't want to be standing on the surface of any planetary body during that time.
Nope.
So, yeah, that's one thing you have to watch out for. Okay.
Okay.
Now, kind of thinking about this, line of thinking, right, is that the recent observation that was done by analyzing ice. So I thought I'd bring this in. And it's not what you're thinking. This is like frozen water.
Ice, frozen ice.
Yeah, we're not talking about people running.
No. I've heard about
We're not
this
talking
story.
about like the Empire and the Empire in Star Wars.
And Hoth and, No. I've seen this story, and this is good stuff.
It is. So what you're doing is you take core samples from Antarctica, the Allen Hills, and that's also a place, notice, that we find a lot of meteorites. So that's like a place that's heavily studied scientifically. And what they can do is do these large core samples and actually look at pockets of air trapped in the ice that was deposited, millions of years ago. And in fact, what's neat about this particular study is that they were analyzing air that was deposited, as far as we can tell, up to about 6 million years ago.
Yeah.
So it's like having a free time machine.
And
right?
Yep.
You go back in time. Think of H.G. Wells in the Time Machine movie, right? You go back in time 6 million years and sample the air, and then come back to the present and tell everybody what did you find, or at least have a sample that's pristine that you can run through our laboratories and give you an idea of the composition of the early atmosphere on Earth.
Right. And people often go, well, how do they know that's that old? Well, number one, we know how fast ice is building up in Antarctica, or how fast it was. So you can tell by the depth. You can also see the layering of it, like tree rings. And so there's a lot of ways to determine how old the ice is. So how do we know that the air isn't just air from our current atmosphere? Because that, you notice it says isotopic temperature. The isotope ratio is different. And we keep mentioning that about a lot of things, but isotopic chemistry gives you a lot of insight to temperature, especially because, of course, heavier isotopes are going to settle out before lighter ones. So water with oxygen 18 in it is going to settle out when it's cold faster than oxygen 16.
And you'll notice that if you go to the next slide, it's argon 40.
Argon 40, which is the decay product of potassium 40.
Right. This is what they're sampling, and we can use that information of how its decay rate to work back and say how old was this pocket of air that they found. And you can see the plot there for yourself. So on the far left side is actually just a close-up as a segment of Antarctica where you see the Allen Hill region and so on. But in the plot in the middle, you have the depth then below the ice as relates to the age as calculated from the argon 40 sample. And notice how far you're going back in time, in the bottom of the plot, till you get to bedrock. And this one particular location in Allen's Hill, It's 1901. It's just a location. You go back almost 4 million years.
Yep.
And then the plot on the far right, this is where we get the 6 million year. That's just a different location, right? And then you can use the same kind of diagnostic tool to use the argon 40 to date the air and that's trapped in this ice all the way back to an extreme time of on the order of 6 million years.
That's it. And notice the delta 18O. Remember I was talking about it on the previous slide. They're basing the composition of the atmosphere and know it's old air because of that ratio, that delta of oxygen 18 to oxygen 16, the more common element.
So this air is 6 million years old, right?
So 6 million year old air.
Wonder what it smells like. Would it smell like rotten eggs?
Well, there's not enough that it would probably detect. Your nose probably wouldn't detect it. Because these are small bubbles.
Can't we reproduce the composition exactly?
Absolutely.
And then we can make enough of it that we could smell it.
Yeah.
I want it smells like rotten feet or something.
Oh, Lordy.
Anyways. Now, the other major piece of information that came out of this study, which is also interesting, is actually the change in temperature. Mm-hmm. So on this slide on the left side, you can see, a picture taken of the core sample, part of the core sample here. That's the kind of stuff that you're looking at. And what they measured was the change in temperature, the delta T, and that's the plot that you see here on the right side. So you can see a significant drop-off in the temperature very early on, way back in that 6 million year time frame. So over roughly, a small period of time, the temperature decline, and they've made a calculation based on the data that they have, that the temperature decreased by about 12 degrees, plus or minus 2 degrees Celsius, over a very brief period of time, 6 million years ago.
Yeah. Now, brief geologically, we're still talking hundreds of thousands of years.
Yes.
Which is part of the problem today. We're not talking hundreds of thousands of years with the temperature changes.
So Robert.
Yeah.
The next question is going to obviously be what?
I'm not sure, but probably
what
about that.
What caused that significant temperature drop, given that roughly 6 million years ago till today, as you see there's been very little decrease in the temperature. It's been trending downwards, according to these results. But what was that huge drop
6 million
way
years
back?
ago? What was going on then? That was one of the increased volcanism times, if I'm remembering correctly.
So this would put a lot of material in the upper atmosphere.
A lot of aerosols.
That would block the sun's light from reaching the Earth a significant amount, and therefore lowering the global temperature of the Earth.
My problem with that explanation is what don't we see? A dramatic rise or a gradual rise back up to those temperatures. So I'm not sure that's the right explanation.
Is it biology?
It could be something to do with biology. It could be due to something. There's so many factors. It can't be the Milankovitch cycles or anything like that going on because those operate on 26 million year time frames.
Right.
So I would have to do some research on the literature of what's being said.
I wonder if there have been any other study using a different technique, of course, or different samples that would have showed the same kind of thing, like some kind of interesting sudden, well, geologically speaking, sudden decrease in the temperature.
And I would say if there has been, it probably involves something like the calcite, because that's seashells and so forth. It goes into limestone. And there's a temperature dependence on, because there's I think the term is isomorph. There's another mineral that is preferred if the temperature is above a certain range, and one that is preferred if it's below that range, and there's an equilibrium back and forth.
I mean, this only goes back 6 million years. I mean, that's not a lot of time.
No,
you think about how long ago were the dinosaurs around.
Which was 10 times that long.
Yeah. So what kind of fluctuations were occurring in the temperature over a time span of, let's say, 100 million years, if we could have had some possible way of measuring that?
We get some information about that from what I'm talking about. There are various mineral systems that have equilibria at certain temperatures. And so we can see how much of that mineral is in one location and how much of its counterpart is in another, and see where that equilibrium lay. and that gives us an indicator of what the temperature is.
But these are really coarse-grained type of
These are
measures,
coarse.
right?
All of it, even this is coarse grained.
Yeah. So you mentioned about, well, why didn't it go back up again? How do we know this wasn't a peak? And so if we go back, I don't
If
know,
we go back before
20 million years, then we're back to the low value that
Right.
we see that 1 million years ago.
right, we may find that there was a peak there instead
Of a plateau. Instead of a plateau or general
Yeah.
trend upwards. Yeah. Very interesting.
So it might have been that it came from a level up to that and then dropped back down.
Yeah.
Absolutely.
Keep digging
Keep digging.
That's-
Keep
that's-
answering,
that's the
asking
model.
these questions and answering.
and keep learning.
That's it.
I mean, go into STEM fields or go into the non-STEM fields, go into any field. Higher education is the key.
Yes.
And one of the ways you can do that, of course, is go to various institutions like our own University of North Dakota. So we have programs both online and on campus. And if you happen to be around, drop in to see Robert and I. More than welcome to talk to you and have a good old chat. In fact, we'll show you the podcast room. There's an
Right.
incentive that if you're around, we will show you where we broadcast live from. And you can look at, like, use Kentucky Fried Chicken Lane in the corner and things. No, just kidding.
Just kidding.
I told you I was hungry today.
Okay.
That's where that comes from.
All right.
Now, don't forget that we will not have a podcast next week because it is Veterans Day. So the next time that we'll be on live will be on November the 18th.
November 18th. Aye, aye.
2/3 of the way through November, the next
No,
podcast.
don't. Let's not go there.
You know what's coming around the corner.
No, it's not.
Yes. What are you
course.
buying me for Christmas this year, Robert?
I don't know.
Hopefully it's
but-
not like you bought me last year, which was nothing.
Right.
Just kidding. I can give you some ideas if you're interested.
I won't be around during
I will
Christmas, so
email you some ideas.
Okay.
Is that fair?
That's fair.
I make sure that they won't cost you too much.
Okay.
A couple $100, no more than that.
That sounds okay.
Now, we always leave you with a quote at the end of our podcast. Instead of telling you where the quote comes from, I
Let's see
want
if
to
I can
see if
guess.
you can guess.
Okay.
Hopefully you didn't look at my paper over
I
here.
didn't.
Okay, good. So here's the quote. And it's related to comets,
Okay.
okay, which we talked about at the beginning of the podcast. I heard much of the comet of that year, 1577, and was taken by my mother to a high place to behold it.
That sounds like Galileo or
Nope.
Michelangelo.
Nope.
No.
Keep guessing.
Newton?
Nope. 1577.
1577.
And he was taken by his mother. So clearly he was a young person
So
at
he was
the
a
time.
youngster. In 1550.
Some famous astronomer.
I can't think
do,
of...
do, do,
I'm going to kick myself when I hear it, but I can't think of who that would be.
Okay.
Sorry.
You ready for it?
Yeah.
Johannes Kepler.
Kepler.
Remembering an event that took place when he was 6 years old.
Wow.
But imagine that he remembers his mother taking him somewhere, where he could have a nice view of the comet of
Right.
1577. Not
Nice.
imagining what happened to Kepler later in his life and what significance he would hold for astronomy in general.
Right.
Pretty cool
But-
when you think about it.
But at the same time, how much did that play into...
Yeah, building his interest in the
Right.
future for sure.
And so we say the same thing for you. Build your interest.
Yeah, exactly. So if you like this podcast, please give us a thumb up, smash that like button, subscribe if you haven't subscribed, and thank you very much for watching.
Thank you, folks. We'll see you next time. Bye.